Good afternoon, everybody. Irfan, can you quickly confirm that you can hear me again?
Yes, I'm online and hearing you.
Great. So welcome everyone to this week's EMinar. Today we have Irfan Akca talking about near-surface EM technologies, archaeological and environmental applications. But before we get to that, and while everybody's coming in, I just want to remind you of a few things about this EMinar. So first of all, depending on how you got to know about this, you might not have seen the MTNet page associated with the EMinar. You can see the URL here at the bottom, and there you can see both the upcoming EMinars but also prior EMinars, and you can register for upcoming EMinars, and where the presenters have made this available, you can see YouTube videos or presentations or both for previous EMinars. So I think this is a great resource, but we're in our third season now, so there's probably more than 30, definitely, maybe even more, nearly 50 talks now that you can look at. We still have 3 open spots, one actually next week and a couple in December. So if you have something that might be of interest to the community, then please contact either me or Alan, and we are happy to host you to give an EMinar. I think if you look through the previous talks, they range from review style talks, and I think that's what Irfan is going to give today, but also some talking about even work in progress or sort of recent results there for turn. So there is no reason to be shy. We are in a webinar. By now, everybody is Zoom expert, I suppose. Probably the only thing that you might not have seen if you mostly spend your time in Zoom meetings is the Q&A button. So the way we typically run these is that all questions should be written in this Q&A box. So it's similar to the chat, but is, if you want, so a different channel. And that just gives us the possibility to have an overview of the questions that are coming in. So far, it always has worked out great if we've dealt with the questions towards the end, but if you have a really pressing question, then I will alert Irfan, and he can answer it in between. If you want to message us about something, I think in the past people have said, okay, the sound is not good, or there's some other technical issues, then you can use the chat for that. And if you have something that is much more effective by speaking, you can raise your hand, and then we can, or I can authorize your audio. So as I said, there are 3 spots available. Next week is one of them, and if nothing changes, the next EMinar will be in 2 weeks by Xushan Lu on surface geometry inversion of geophysical electromagnetic data. But yeah, as I said, please come forward if you're interested at all in giving one of these EMinars. So yeah, coming back to today's speakers. So as I said, Irfan Akca, and he has MSc and PhD degrees in geophysical engineering from Ankara University, and has been working on all kinds of aspects of inversion, including genetic algorithms and parallel computing and visualization. And recently he started to work on archaeological methods with GPR and other types of geophysical surveys. And I suppose some of that work is what he is going to talk about today. And at the moment, he is a researcher at the geophysical department of geophysical engineering department at Ankara University. So with that introduction, I will stop sharing and hand over to you, Irfan.
Okay. Thank you very much, Max, for introducing me. Is my screen shared at the moment? I don't see it.
Yeah, right now I don't see it yet, but sometimes it takes a few seconds. Yep, something is coming. And yes, I can see your full screen. And I can hear you, so I will mute myself and stop my video.
Okay, thank you very much again. I want to say good afternoon to everyone joined this EMinar. For sure, good afternoon is for my local time, and I want to say hello to everyone. This talk was already presented at the 25th EM workshop in Çeşme, Turkey, last 2 months ago. And I will repeat it. I didn't add anything. So if there is someone already seen this presentation or listened to this talk, it will be the second time. But I want to thank everyone who joined this meeting to listen to me. Okay, I am going to talk about near surface applications of EM technologies, mainly the GPR or ground penetrating radar method. Although the title includes archaeological and environmental applications, I will mainly focus on archaeological part because we held this workshop in a touristic and ancient part of Turkey, which was at the time of the workshop we organized. So let's start. The content of my talk will be an introduction. After that, what are near surface applications we conduct using electromagnetic methods. After that, what's archaeological prospection. And I will talk about the recent developments in GPR measurements, which are mainly applied for exploration of archaeological targets. And I will give examples from the literature. Finally, I will conclude about the developments I have summarized in my presentation. Okay, let's start with the definition of near surface term, because there has been also made some reviews about near surface applications, but this near surface is not a strict word, so it may change from one to the other. So in SEG's one of the papers, it's defined as the upper few meters to 100 of meters of the Earth's crust is defined as near surface. As you know, we are trying to explore the whole diameter of the Earth. So the near surface is a very, very small portion of the Earth's crust compared to the whole globe. So as I already mentioned, it's a relative word that the near is used. So for example, Mark Everett defined it as smaller than 1 kilometer. But in this talk, I will limit it to the 10 meters. So we may call it as very, very near surface. Okay, what applications we do in this scale? I mean, the very, very near surface. First of all, we conduct applications to determine the concrete quality, road bridge pavements, civil engineering applications, or unexploded ordnance detection, or infrastructure applications, or forensic investigations is another area of application, or agricultural investigations. These are also ordered in the depth scale they reach. So these start from several centimeters to 100 meters, but our focus will be again on the archaeological prospection, which is limited at about 10 meters depth from the surface. Okay, let's continue with archaeological side of this talk. In many parts of the world, we have archaeological remains which dates back to thousands of years from today. Turkey is also a rich country about regarding with the archaeological history or places. So there are very attractive locations in Turkey also, which are very famous in the world also. One of them is the Göbekli Tepe, which was discovered in last decade, and it's changed the history of the human we know about the development of the humankind. So there are very first or early examples of the civilization in Turkey. For example, Çatalhöyük is one of the first places where people growed wheat, which is used for cooking bread. Also, you see a map of the city at that time, which we see a volcano in the background, which is close to here. I don't know if my mouse is seeing. So it's one of the earliest maps of a city, and also a volcano eruption is reported. Also, we have a lot of places which are remembered with philosophy or science. And also we host the city of Troy, which is also a famous place in world history. Okay, another place in the middle of the country is the Hittite Empire, the capital city of Hittite Empire, which is my also hometown of my parents. Also, this sun disk you see on the top comes from that place, and it's our university's logo. Anyway, I want to just introduce what's archaeological prospection and what's the place of geophysics in the archaeological prospection. An archaeological excavation can be conducted only once, and it destroys the place the archaeologists study irreversibly. You cannot make an excavation twice, or you cannot make it back, turn it to the original state. So the European Convention admits the scientists to work with non-destructive methods of investigations whenever it's possible to apply. And geophysical methods like as magnetic, resistivity, and electromagnetic may provide these non-destructive applications to explore the archaeological places. With using these methods, some targets we try to explore is graves, walls of any structures, any architectural structures, cavities, or submerged features which are now underwater. Maybe the possible targets of an archaeological or archaeogeophysical investigation. I want to show an example in the beginning. You see two sections on the left of the screen, which is a resistivity depth slice at top, and a GPR slice, time slice, which is also converted to depth at the left bottom. So this is a very typical example which is conducted by our geophysical team. You can see a depth and make suggestions to direct the excavations, and it's for sure it's a non-destructive method. In the example, this example belongs to a city of Patara, which is in the southwest of Turkey. And when they excavated this area, they found a basement of a monument, which is also clearly seen on the right. It's a 4x4 sized monument basement. So we also apply different methods like resistivity and magnetics to explore archaeological remains. This example on the left is also conducted by us, and it's also another famous city in Turkey, which is called Side in the original reference. And the model, the 3D model you see in the left is a resistivity model after a 3D inversion case, and it shows the geophysical results of a site with a size of a football playground. It's 60 by 100 meter wide, so you can clearly see the traces of embedded structures in this area. More examples, more very successful examples may be found in the research literature, and another one is also maybe seen in Al-Saidi et al. It's a very high definition or high resolution resistivity map, which is also showing very clear evidence of archaeological structures. Magnetic method is another popular geophysical method which we use in archaeological prospection. You also see two very good examples of this method. The one on the left is conducted at Egypt, a tomb site. You can see a lot of anomalies which looks like a map directly, but none of these structures are on the surface. They are underground, so you can clearly see the whole site for evaluation. The one on the right is from the Stonehenge from England, and the maps here are showing other structures around Stonehenge. Okay, resistivity and magnetic methods really make good support to explore archaeological places, but our topic is related with EM, electromagnetic methods. So they have some drawbacks also, because magnetic methods do not provide depth information, and application of resistivity method is time-consuming and requires a labor. Several workers is needed to conduct or to scan a large area. So let's continue with other methods. I want to say some words about the history or the development of archaeological prospection using geophysics. It started around the 1940s. And at that time, according to the technology we have, a sign of the presence of any structure was very valuable and enough. But further, we had more sophisticated devices and methods, and also data processing abilities. So we can produce sections or maps around 1980s. But after 2000, in second millennium, I think that tomography or 2D, 3D sections or models became a standard in this area. So we started with a spoon of honey, but now the archaeologists wants or request the whole jar of the honey. So, and we are trying to reply their requests. So at that point, we reach to a point that what method we need, or what's the expectation of archaeologists from the geophysicists. They or we maybe try to optimize the 3S. These 3S are coming from speed, sensitivity, and spatial resolution. The requirement of development in these three topics is always in the diary. So we are always trying to optimize these three issues. The ground penetrating radar or GPR method satisfies these three tests. It's a method that we can conduct it in the speedway. Its sensitivity is high and it provides high spatial resolution. So it became the main method used to explore the archaeological places. I don't know if everyone is familiar with GPR, but I want to make a basic remember slide here. The GPR method, ground penetrating radar method, is a high frequency electromagnetic method. So it has we emit high frequency EM waves to the ground from a transmitter, and we record it by a receiver where the waves are reflected, refracted, or diffracted from different environments or objects. This electromagnetic method, therefore, is a time domain method where the traces are recorded as a function of time. In the middle, you see a sample trace, which includes reflections from subsurface layers or targets or objects. So if you drag the system of transmitter and receiver in the lateral direction, you can then have a series of traces, and which produces a radiogram, which is a section of time series we recorded by the receiver. Okay, at the moment we have a lot of instruments produced by different manufacturers, and the frequency of the GPR equipments range from nearly 3 gigahertz to the 12 megahertz. Depending on the frequency range of the antenna we use, the resolution and penetration depth changes. The higher frequency means higher resolution, but lower penetration. But in the opposite, if you use a lower frequency, then you can penetrate depth, but your resolution is getting worse. So we have a transmitter antenna and a receiver antenna. And as you see on the top right, the receiver and transmitter antenna becomes bigger when you decrease the frequency of your equipment. So the antenna is getting bigger to produce that wavelength or the frequency content. At the bottom, you see some different kind of GPR equipment, which are named as shielded antennas. These antennas are in a shield, so they are protected from the receiving or the reaching EM waves coming from air or ground surface, because we want to record the traces coming from subsurface. So they are shielded, and it provides a protection about noise sources and also the waves not coming from our target. Okay, this application of GPR method is also not very old. It do not go very old. So first examples are in 1970s. After that, it continuously gained popularity in the archaeological prospection, because it really provides high resolution subsurface images. In this slide, you see application of the GPR measurements in the field. On the left, the equipment is triggered by a wheel. So when you move the antenna or drag it, it continues to measures or transmits and receives EM waves. And you see a sample radiogram on the left bottom. where you see very typical hyperbolas coming from the subsurface targets. We see the anomalies of subsurface targets usually as hyperbolas because the travel time equation is a hyperbolic equation. So you see hyperbolas everywhere in this section, which are coming from different targets of archaeological targets. Okay, if you make several measurements which are parallel, like the ropes you see in the right picture, then you can produce a 2.5D or maybe 3D model or tomography of the subsurface. If you continue measurements with a spacing on the other direction, then you can conduct or produce a map, a depth map or a depth slice or a time slice, because we record the radar signals in the time domain. So it may be a way to measure in both directions, maybe in perpendicular directions, or in parallel to produce a model like shown on the bottom right. This is a very typical example what we have after doing everything right to explore a subsurface structure. It's coming from Siena, Italy, and the research or application is conducted by Campana et al. And you see a Roman villa which is underground. It's nearly 1 meter depth. You see a slice of 1 meter depth from surface. So you can see a very clear anomalies of the walls or structures which are underneath the surface. Okay, what developments we follow about the application of the GPR method in the archaeological measurements? Am I still online? Is there a problem?
Yeah, it seems fine, sorry.
Okay. I have lost the Zoom screen, so
I can see your development slide.
Okay, no problem. I will continue. Okay, we follow this developments in the following topics, which is survey speed, measurement sensitivity, more spatial resolution, and also we try to make some new application areas for the GPR method. Okay, specialized cards is helping us to speed up the measurements. Multi-channel GPR systems is another development which also increases the resolution and the survey speed. For the rough terrains or large areas, now the main development may be referred as the airborne GPR, which is containing the or loading our GPR equipment to the drones. And also we in the latest case we are sending GPR systems to the other planets like Mars, or also we are conducting some research on the marine or submarine environments for exploration. We are also using the GPR method or electromagnetic methods already in this environment. Okay, in the beginning, the application of GPR when started, then we thought that cross-line spacing of 50 centimeters was a high resolution measurement. Then we tried to decrease this distance, so we can now use 5 centimeters of cross-line spacing, which means we have traces, adjacent traces where the spacing is just 5 centimeters. And also, it's for sure it's dependent on the frequency we use. I mean, the trace spacing, also the line spacing is dependent on the frequency we used. As you remember, the frequency, the lower frequency means higher penetration depth, and the higher frequency also provides the high resolution. So the trace spacing and line spacing is set up accordingly. Okay, the cards or the wheeled cards helps us to speed up our measurement. You see an animation on the right, which is also recorded by myself. This researcher, the geophysicist, uses this card to quickly measure lines. But in that case, real-time location definition is required. So this type of measurements is equipped with a real-time GPS receiver also. So it records simultaneously the location of the trace. So you can now have a path like the one on the left, and just a man can scan an area of 5,000 square meters per day. And this increases the speed of survey. It's a practical solution. The 3D tomographic model here also is produced by our team, and it belongs to the city of Patara, which is the hometown of Santa Claus. You see that the anomaly is in the red color scale, and when you produce isosurfaces of these amplitudes, higher amplitudes, then you can see the whole map of the area where you see structures embedded underground. So yes, the measurement is important, but also we need some data processing applications and visualization methods to produce the final geophysical images or models. This is a very good example, I believe. I just put this example today because I was just processing a new data set from a new area, and you can see a depth slice from surface to the bottom. And in here, you can see a circular shaped basement of a temple here. I just have this result today. It's a very new example. Okay, the cards type differ from to manufacturers to manufacturer, or so there are a lot of examples. They are all good examples. Some of them are more compact. Some are others are more suitable for rough terrains. Also, depending on the frequency of the antenna, its size is also changing. So there are a lot of good options to use with cards. Okay, the second tool we have to enhance our speed or resolution is multi-channel GPR systems. Multi-channel GPR systems mean we use lots of antennas simultaneously to record GPR signals or waves. There are different options to send, transmit, or receive the EM wave. Also in here you see some towed options, towed devices here. It's towed by a motor vehicle, or some of them are also operated by human still. But multi-channel GPR systems became heavier and not easy to carry it by hand. So a supporting vehicle is usually required. Okay, these are the options we have to use a multi-channel GPR system. The first one is multi-static. That means we use sequential transmitter-receiver couples. We use first the one and the other one. We use sequential shots and receivers. This one multi-static method is this. So we can have 8 to 25 channels at a time, and you know the measurement is in a time range of nanoseconds, so we can fire up a lot of shots sequentially. The other option is multi-offset. In that case, we use just a transmitter and lots of receivers at a time. This is more close to 3D the data measurements, because it's also spans the third dimension. Okay, with increasing the data volume size and the spacing, more sampling rates also requires good location information, because we will have lots of traces in some centimeters. So, and the great location information is also required. So it must be also supported by such a GPS system where all traces are on the right location. Otherwise, you can have wrong anomalies which are not in the right location. Okay, I will show some examples produced by multi-channel GPR systems. The one on the top is measured with a single-channel system, which is also a successful one. But after using a multi-channel system, you can have an enhanced image of the subsurface where you have very detailed information about the structures underneath. So it's sometimes very important for archaeologists to have some details about the structures. So yes, it's very useful to use a multi-channel system. Enhances our resolution. Okay, the multi-channel systems are also used in the snow environments like the poles or climate explorations or investigations. This example is from an application where the snow cover is tried to be detected. The one on the right is from a single channel system, and the left is from a multi-channel system where we also see an archaeological target. It's the circular one on the middle. Okay, let's make a overview about multi-channel systems. Yes, if you use a multi-channel GPR system, it provides more resolution, and also if it's equipped with a motor vehicle, it also increases the size or the area with scan in the unit time. For example, just a vehicle here you see in the picture may scan 1.5 hectares per hour. It's really a high amount of area scanned. Also, we can decrease our resolution to centimeters. But in the contrary, these devices produce a really huge amount of data because of the multi-channel approach, and also need to be processed. So you need a high computation facility to process this kind of data. As you see in the picture, these antennas are heavy and cannot be put in your car's luggage. So it requires some logistic developments. And it's also, as you see, its size, it cannot be used in the rough terrains because it cannot be, its obstacles are preventing these antennas to use efficiently. Okay, the other development may be mounting GPR systems on the UAVs or drones. As you all know, we conduct EM measurements as well as gravity and magnetic methods airborne. It has a very wide area of application and very successful applications we have. But the GPR systems are lately became popular to be mounted on a drone. What are UAVs or drones? There are several kinds of drones or UAVs. They may be classified as single rotor, fixed wing rotor, tricopter, hexacopter, quadcopter, and fixed wing hybrid vehicles are some examples we see in the industry which are used for different purposes. And these drones or UAVs are equipped with some kind of sensors like LiDAR, like different kinds of cameras, spectral or hyperspectral cameras, thermal cameras, and magnetic sensors are already mounted on these vehicles and used in different kind of science, already also in geophysics. There are some UAVs or drones which may carry up payloads of 100 kilograms, which you see on the top right picture. They are also used in delivering some parcels, or there is a lot of application area of the drones. Some applications which are already used in archaeological prospection is for example, you see a magnetic measurement device which is mounted on a drone, and the results are compared in the bottom. The one on the left is a ground-based magnetic measurement, which is conducted in the Oldenburg, France, and you see very clear image of subsurface, which we see archaeological structures under the ground. And the one on the right is equipped with the drone-based magnetic measurement system. Yes, it's not as clear as the one on the left, but it provides clear image, which is also interpretable or beneficial. Remember that you do not use a human operator or in the one using the drone. So it's very quick one, it's very efficient one, and it's a little bit worse than the one on the ground surface. Similarly, we use some special cameras like thermal camera and spectral camera to detect archaeological features which is embedded in the ground, and they are also good options to use in this area. Yes, we have airborne EM methods, but drone-based systems are not as old as the other ones. So there are some examples conducting EM measurements and T measurements, which are presented by Stoll et al. And Kotowski et al. There are some special drones and sensors which measure EM quantities. Regarding the GPR method, we recently have some options which are produced by some commercial companies, and also there we have some examples from academic community also. But this method or the approach is like we have two approaches in this area, which is the GPR is on board. That means it's a part of the vehicle. The other method or the approach is using the drone as a carrier, and we have just simple GPR antennas used on the ground, mounted on a flying device, especially drone. Okay, I will show some very basic examples about this area of application. For example, Garcia and Fernandez used a high-frequency GPR system to detect unexploded ordnance, which is very close to the surface. Because of the frequency we used, the penetration, the depth of the GPR method using drones is not very high. So it's mainly focused on very near surface targets. I will not go deep in these applications, but I will refer to the Noviella et al. to a very good comparison of the drone-based or UAV-based GPR systems in several topics. They compare all of the abilities or the availabilities. In the second part, the second type of equipment are, or the approach is mounting a ground antenna, GPR antenna to a drone. This is that example. So some radar antennas are mounted on a carrier and applied to explore the subsurface. But as you see, the frequency is differing between 90 to 120 and 260 megahertz, which are low frequencies for detecting archaeological targets. It's not enough. We need more higher frequencies to detect archaeological targets. Another device produced by Mala is also available, but its working frequency is 80 megahertz, which is not very suitable for archaeological targets. Yes, it provides a lot of things, a lot of benefits to use a GPR-based, drone-based GPR, but there are also many drawbacks like the navigation or flight dynamics. The drone must be stabilized because the trace, the measurement range is in nanoseconds and trace spacing is in centimeters. So we need a very stable flight. And on the other hand, we have an air layer between the drone and the ground surface, so it produces clutter effects, which decreases the quality of the data. Okay, so there are some examples conducted using GPR systems mounted on a drone. For example, this example is from a snow cover mapping application. There are two radograms on the right bottom side, you see. The one on the bottom is from a ground-based measurement, and the one on the top is from the drone-based measurement. It's normal that the ground-based measurement is more clear and noise-free, but the one on the top is also an acceptable radar section. As you see, the depth of penetration is not more than 2 meters. And also we have two hyperbolas here, which are maybe some stone rock presence. Okay, as I said, there are a lot of examples of drone systems mounted on a GPR drone, but at the moment, we are far away from the results we expect. For example, this example is from another application from Italy, I guess. The one on the left side is the sections time slices or depth slices after processing the GPR data. It's a very big area with size of 100 meters around. When we conduct a drone-based GPR measurement on these features, these anomalies, yes, this result is present on the top right corner. You can see the hyperbolas, which are coming from the subsurface targets, but this image is not clear as we expected or requested. So that means we still have some way to use drone-based GPR systems to have better results at the archaeological sites. So let's again summarize the UAV-based or drone-based GPR applications. Yes, autonomous or different types of UAVs are getting popular. They are developing and they really do good job in many areas, but today's situation, the systems are more suitable for the application of UXO or landmine detection or snow cover detection, but not as good as for the archaeological prospection. This is because we need high frequency antennas, but also penetrate. They should also penetrate to a higher depth. So the problem is to produce an antenna with good frequency range and also penetrates to the required depth. Okay, there are also some other applications where we see in the latest years. For example, autonomous land-based or ground-based vehicles are used to measure GPR systems. You see a device here which is mainly designed for agricultural applications, but at the moment it's equipped with a multi-channel GPR system. So it scans a big area of investigation area autonomously. It's programmed in the beginning, so it travels around the field and measures GPR data. There are also some good applications with such ground-based vehicles. Also, we have some examples using such kind of ground-based autonomous or man-operated vehicles. For example, this example is from a polar application. You see a radargram which is measured with a special motorized vehicle. It's called Yeti. And a 400 megahertz antenna system is used to measure this data in Antarctica. So the traces you see here are coming from an old scientific building which is now under snow cover. So there are a lot of traces here, and the structure is known, so we can define which anomaly comes from the roof, the science tunnel, or antenna. It's interpreted. Okay, we are coming or approaching to the end. We also have good examples or several examples where we conduct GPR measurements on the top surface of the water level, or sometimes underwater. We can use the same devices or antennas on the top of the water or on the surface of the water. For sure, we need to take some precautions to protect the devices from water. Apart from that, we can use the same systems to measure the data on the water, but it's required to note that the GPR is dependent on the electrical properties of the medium. So in sea environment, for example, the EM method will fail and not work because of the conductivity and the electric properties of the water. This is a good example from the literature because a real size of the laboratory tests are conducted for underwater research. It's a modeling or approach. It's conducted in the laboratory, but the scale and the design is very, very close to the real cases we usually have on the real experiments or surveys. So I may refer this work for further details. These are the results came from their applications. Yes, the water on the top makes it difficult to image the structures which is on the water. And this example is from China. It's a submerged archaeological place that they are looking for some kilns, which is ovens, which they bake ceramics or clay-based materials they built. So it's also a very good example because we see also the bottom of the water or the lake, and also the anomalies coming from the submerged structures here you see. Okay, I am now concluding my talk. Okay, we have a lot of electromagnetic methods which are also conducted for near surface applications, or namely the very low frequency, horizontal loop EM, time domain reflectometry. And GPR is dominated all of them because its development fulfilled the 3S requirements, which are speed, sensitivity, and resolution. We have a lot of examples where successful examples we use GPR method, and for investigation of archaeological sites, I am providing a list of literatures at the end. Because of the success of this method, imaging near surface in 2D and 3D become a standard, and we further developed multi-channel instrumentation, and we are now trying to mount them on the UAVs or drones, but that still needs some developments to be used in archaeological investigations. The data process of GPR data reached still a standard. Yes, we have all tools we need to process these data sets, and we produce nice results. But regarding the visualization, we still work on that part to more clearly present our results. The UAV-based EM systems are useful for detecting very, very small and near surface targets like UXPRO. And but UGV, I mean the ground-based vehicles, are good solutions for ground-based autonomous GPR measurements. In the freshwater environments, we use GPR methods for also imaging the bathymetry of the lake, for example. And also the target of targets like archaeological remains which are submerged are also good targets for GPR applications. Okay, I want to thank all of you for listening to me. I have a list of references here which I may share with the audience, and I will be glad to answer questions if there is any. Thank you very much.
Thank you very much. That was very interesting. Yeah, we already have a couple of questions. And the way we typically do this is I read the questions and then you answer them, so that when people watch it on YouTube, that those questions are also in the record. So there was one question which actually, I have to admit, I missed during the talk. You talked at some point about 2.5D. So that person is asking, what do you mean by 2.5D? Okay, we measure the data just in line, but when we try to visualize it, then we produce a volume. So the signals are not coming from a 3D approach, but for example, in this one, the data is measured on lines.
not using multi-channel systems, but when we combine them to produce a volume, then it may be referred as 2.5D because we try to see the continuation of the structures in the other lateral direction. It's not 2D, but also not 3D, so we can refer it to 2.5D.
Yes. And the second part of the question by the same person, how to fix the speed of GPR during the survey? I'm not sure which speed that person is referring to. I suppose how you drag it across, or I'm not sure.
Okay, as I already mentioned, the measurement, for example, using a 500 megahertz antenna, the trace length is just 100 nanoseconds. So you can measure a lot of traces just in a second. In some cases, the speed is controlled by the wheel you see here. When it moves, you can set up the device to fire at every 5 centimeters or 10 centimeters or more or less. So it can be controlled by the wheel. When you move the antenna or device, then it fires according to your walking speed. So it's controlled by your setup.
Okay. Mm-hmm. And then I suppose another person is asking, what are the ideal field and weather conditions for GPR data acquisition?
What should be the ideal weather condition?
Yeah. Irfan, are you still? Yeah.
The connection is slow, I guess. But if I understand correctly, the audience is asking what is the best weather conditions or the ideal weather conditions to.
Okay, it seems we're running into some connection problems. At least on my side, your video and sound are frozen now. I'll give it a few more minutes, few more seconds to see if we can come back. Nope. Okay, that is very unfortunate because it seemed like we were getting quite close to the end. Yeah, I'll wait 30 seconds or so to see if he can rejoin us, or if I get an email. Yeah, that is very unfortunate that he got interrupted and cannot finish his presentation. In any case, I would like to thank Irfan for his presentation, and for everybody else. I suppose the best way to approach this is to send him an email if you have any concrete questions. There will be, unless somebody volunteers, no EMinar next week. So I will see you all back, I hope, in 2 weeks for the next EMinar. I just have to look up the time again. Just 1 second. Okay, now my technology also doesn't want to play ball. At the same time, so 2 o'clock Universal Time in 2 weeks, we'll have Xiushan Lu talking about surface geometry inversion of geophysical electromagnetic data. So thank you all for attending and hope to see you in 2 weeks.